All right, so what we're going to be doing today is we are going to be going a bit farther into probability. Last time, what did we discuss? Anyone? What did we talk about last time? Yes, Aiden.
Bayes theorem.
Bayes theorem. What is Bayes theorem?
Probability conditional probability. So the probability of something given there's another thing happening at the same time or along with it, and also probability of it not happening.
Yeah, and so we had this great equation that I'm sure you memorized. Right, yeah.
You have to memorize that one?
No, I don't want to be there, don't worry. But it's a great thing to memorize, though. It's faster to memorize it. It'll be on the final view. But you should at the very least remember the notation, because I've seen people too where I give people the equations, but they don't know what I mean part of it, because they're like, oh, it'll be on the thing, I don't have to remember. But then they don't know like what all the symbols mean, so they functionally don't know anything. So this is of course the conditional, assuming B is happening. What's the probability of A? This is just the probability of A. And what does the tilde mean? What does this mean? Not A. So we're gonna now pull away from this conditional idea, and we're gonna dive into something a little bit more complicated. Not bad, but a little bit more complicated. But the thing that we're gonna be essentially focusing on is that probability of A. Except we're gonna redefine it as probability of X. Before, this probability was sort of an on-off switch. If something happens, if it doesn't happen. Right? What is the chance that someone is on drugs, or someone is a terrorist, or someone is a nerd? Now we're going to do something a little different. We're going to use X, where X will be a number. What is the probability of 3 people showing up? Or what is the probability that 50 coupons are redeemed? And in order to understand that, we have to recognize that X represents many things happening or many things not happening. In other words, we're not concerned about the number, although the likelihood, not just the likelihood that something happens, but the likelihood that many things happen. The chance of a certain number of successes. Now, to be clear, success does not mean something good happens. Success is simply a terminology we use to say this was interesting. This is something notable. This is just a nomenclature. So we're working with the probability of a success, and then we will ask things like, well, what's the likelihood that a certain number of successes happen? So there's 2 levels of probability we're working with. Now, can you have half a success? If I say, what is the chance that 50 coupons were redeemed? Can you have half a coupon redeemed? No. So, in other words, successes are never partial. Can successes ever be negative? No. Why do you say no? Like, can we have like -3 people show up to work one day? No, I don't even know what that would be. Right? That's weird. So, success is never partial. Success is never negative. Success is what we call Whole numbers. What's a whole number?
Remember? What a whole number is?
Give me a hint, right? We have
Greater than 0. We don't have to estimate one.
natural numbers, a little different. That's close. Whole numbers. I'm trying to remember what the next one is. I think it's integer, rational number, and then a real number. Do you remember seeing something like this from back in the day? You're nodding your head, CJ. Yes, you remember this? So what does this represent? Like what is a natural number?
It's like 1, 2, 3,
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to, whatever infinity is. So what would be a whole number?
It's natural number plus 0.
Yep, exactly. Natural number plus 0. So I guess they don't consider, because I guess like for historical reasons too, 0 was sort of a weird concept for a lot of history, for a lot of human history. People were like, how can you have nothing? You have hand, how can you have nothing? So we don't consider it natural. Mathematicians don't consider it natural. They have funny names for things. But then this whole, and then we can go into things like integers. What are integers? What do integers include? Negatives, exactly. What is defined as a rational number?
Yep, that's nice.
Yep, now we can get into the partials, right? So, and what, by the way, then what would be real? What's the difference between a real and a rational number? So what would you say? So I would be imaginary, right? So I would be not real. I know, right? Math is weird, and the terms I have for stuff is strange. Well, that's not really a number. That's an imaginary number. What the hell are you talking about, right? Of course, if you know your math, when I say imaginary number, I mean square root of -1 is I. So that would not be included in real. But what would be included in real are rational and irrational numbers. What's an irrational number? Pi is an irrational number. E is irrational. Square root of 2, irrational number. Fun fact, irrational number is defined as a number that cannot be written as a fraction. And don't give me that shit like, well, I can write pi as a fraction, say pi over 1. I think you're cheating. Don't do that. So, why do I do this? I do this to help define what I mean by the kind of distribution we'll be working with. We are going to be working with discrete probability distributions. Discrete probability distributions are only made up of whole numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Because discrete probability functions work with successes. We are cared by how many successes we have. We should make this distinction between discrete probability functions and continuous probability functions. Continuous probability functions work with real numbers. You can, an example of a continuous probability function would be a normal distribution. We can have any number of values. They can be negative, they can be positive. You can theoretically make pi pounds of food. You can have like pi pounds of blueberries, arguably, right? It would just say 3.14. I don't, you won't be able to prove it because the scale won't be precise enough, but theoretically you could, right? So it includes all the numbers. It includes all these real numbers back and forth. They're on the number line. We're not working with continuous, though. We're going to be working with discrete. There are going to be three different types of discrete probability functions we'll be looking at. I'm going to define them all for you right now, and then I will show you how to use them in Excel all at one point. So, because I don't want to have to bring this up and down, sometimes I do it with like we define one, and then we show you in Excel, then we define another, and we show you in Excel, define a third, show you in Excel. That back and forth, I have to bring this thing up and down a lot. So, we're just going to define them. We're just going to define them now. In general, they are binomial, hypergeometric, and Poisson. Binomial, hypergeometric, and Poisson. Oh, here it is. Let's imagine I was curious. I wanted to know, I issued maybe 1,000 coupons. I want to know how many coupons would I expect to get redeemed? If I wanted to get an idea how many coupons I would expect to get redeemed, what would I have to have some idea on? What I have to know? Yeah? Gabe? Yeah, okay, absolutely. So I have to know how many were issued, how many I sent out. So I don't know how that. Obviously, I know that, 1,000. What else would I have to know? Think in terms of probability.
How many people actually shop at the stores?
Okay, what would that tell me?
You know, like, if you only had a couple people that shop at the store, probably people would
And other things too will affect that probability too, right? Not just how many people shop at the store. Like maybe if there is a recession, people are more interested in saving money. They're more likely to redeem a coupon, right? Or maybe what the coupon is used for is really, really valuable and people would love it and they're more likely to redeem it. Or maybe it's a coupon for like, I don't know, like an onion shake or something and no one wants it. It reduces the likelihood. But generally speaking, what I need to know is the probability that the coupon will be the probability of an event happening, the probability of success. In a binomial distribution, the defining aspect of it is the defining characteristic is the probability of success is constant. So for any given trial, for any given observation, the probability is the same for all the other ones. It doesn't change based on the result. Just because you redeem the coupon does not make it more or less likely you will redeem the coupon. So a binomial. And I again remind you, success is just a nomenclature. There's no value judgment here. I'm not saying that successes are good. I'm saying successes are the unusual thing. Successes are trying to get what we estimate essentially. So if you're pulling cards from a deck, I want to know what's the probability that I will pull an ace. Is that a constant probability? As long as I put the card back. Excellent. Right. If I do not put the card back, if I draw 3 cards, after the first one, the probability of success will change than before the first one. If I pull a card from the deck and it is an ace, that means the likelihood of me pulling another ace has fallen, right? Because so now there's only 3 aces left. So if I pull a card from the deck and it's not an ace, that means the likelihood I will pull another ace has risen because now there are fewer failures in the deck. There are fewer non-successes. But if I replace them after I draw and shuffle it up again, then that probability doesn't change. Cross trials, I should say. Cross trials. We have one little wrinkle in that. The probability of success, we can be treated as the same if the sample size is small, the number of trials is small, compared to the population. So let's imagine, for example, that I shredded some documents and I wanted to be extra careful and I put those documents in maybe 2 different bags. And then I put these bags and I threw them away with 1,000 other bags of trash. And then I said, "Sure, but I didn't want to shred that document. I need to get that document back." And I go to the landfill and I start going through bags. If I pull one bag, the chance of me changing the probability of my success is really small. If I take not 1 deck of cards, but 100 deck of cards and put them all together, and I pull 3 cards, the chance of me changing the probability for any one, or the probability change that will occur once I pull a card from the deck will also be very small. It will be functionally no change at all. So when we say that the number of trials is small compared to the size of the population, we say, well, that's close enough. It's like technically not the same, but it's close enough. And so when n, or our sample size, is small, it's binomial even if the probability would change, or if the probability could change, technically. By small, I mean less than 5% of the population size. So less than. Any questions so far? The average number of successes is pretty straightforward. It's just P, which is the probability of success, times n, which is, of course, our number of trials. Or our sample size. No, I just wanted to mix it up some, so I probably shouldn't do that. I thought the blue was clear, but I don't want to. Now you maybe want to use it more. I think I actually want to put n first anyway. don't do that yet. Don't want to do that anymore. P is the probability. I mean, it doesn't really matter because you're multiplying it, but just make it look nice. Sigma is the square root of n times p times q. So I want to take a guess as to what q is. I'll give you a hint. Yeah?
Is it, so his probability Q is
Yeah, that's where you're going with. So what's q?
the opposite, so 1 minus B, so Q is 70, Q would be 30%.
Mm-hmm.
It's like,
So we would call it the probability of failure. I took your thunder away, Dave. You were already there, and I was writing it down. Any questions? Okay. Hypergeometric. I'm gonna do the hypergeometric stuff right here. Definitionally, it's pretty straightforward. It's just the probability of success is not constant. Because it's not constant, I cannot use this, I cannot use P anymore in my abbreviations. Why not? What do you suppose that is? Because P keeps changing. The whole point of these equations is I am trying to figure out Px. What is the likelihood I will get 10 successes if I do, I don't know, 20 trials? Well, if the probability of getting a success changes from one trial to the next trial to the next trial, then I can't just put in a one value of P. Because it's going to matter how much P changes. So I'm going to have to work with the component parts. If I want to pick someone at random from this room, and I want to say, oh, I want to pick someone at random who, I don't know, likes cats. Who is a cat person? Raise your hand. Wow, no one likes cats? It's a bad example. This won't work at all. Really? Oh, you like dogs? I don't like dogs. Well, I guess it'll be me. Pick myself. Who likes dogs? Really? Literally everyone? I should just use something else. Why do people like dogs so much? I don't get it. Reptiles. All right. Yeah. My cat likes me back. She just doesn't require very much of me. That's what I like. All you people who like dogs, you don't like dogs very much. We have to get up in the ass crack in the early morning when you can walk it, do you? No, you don't. Yeah. Yeah. So I always like my cat. Fine. What is the? Let's see. If I use iPhone, you probably all have iPhones too. I was going to do that. What is the probability of someone who's been out of the country in the past year? There we go. How many of you have been out of the country? Okay, so about half. Thank you. There we go. If I were to, what was that? Well, I think it was about half. Now, how would you calculate what's the probability though? I would ask you, what was the probability if I pick someone at random? What would be the probability of picking someone who was out of the country in the past year? How would you figure that out?
People that have been outside the country divided by like total people.
Ah, you mean the number of successes in the population, which we'll call R, divided by N, which is our size of the population. we agree that should equal the likelihood that you grab somebody, right? That you selected someone. Now let's imagine I select someone 10 times or 5 times. Let's imagine I select let's imagine I select 6 people, and R divided by N is 0.5. If I select 6 people without repetition, on average, how many people do you think I'll select that were out of the country? No, but on average, right? It shouldn't matter. Right. I'm just saying, on average, if I were to do that and I were to do it like 1,000 times, what would you expect? Pulled 6 people, maybe I pulled them all at once. Three. Yeah, there's no trick here. It's 3. So there is actually no real difference between this and this. They're basically the same equation. Maybe I should put the N in front just to highlight that symmetry. Because R divided by N is really probability. The issue is when we talk about what is the likelihood of getting 3. That's when things get complicated. But on average, I would expect 3. How likely that average is a different question entirely. But on average, I would expect 3. So this is very similar.
Any questions?
This is where things get nuts.
Well, actually, I like this. That one is n minus n minus 1. I believe I want to make sure I do this right.
Yeah.
That is, that's also square root, and that's n r. That's square root n r.
I shouldn't try to do this from memory.
No, I was right.
It's small n. It's small n and big N. And then that is n squared. So I'm going to rewrite that because it's a little messy. Sorry about that. It is small n times big R, big N minus big R, n squared, square root 0. Make sure I wrote that down right.
Multiply the 2 square roots together.
Why? Because it's just how, shut up. You could obviously simplify this by making that just n rather than n squared and moving that square root to the top exclusively. But there's enough going on in that equation. Again, obviously, I won't have you memorize it. Hell, I can barely memorize it myself. I got some parts wrong. But it's just a plug and chug. Once you have the equation, it's just plug and chug. Just the standard deviation is going to be the number of trials times the number of successes in the population times the difference between essentially the number of failures in the population, so the size of the population minus the number of successes, divided by the population squared, and then you take the square root there over the whole thing. And then you do the difference between the number of population and the trials, divided by the population minus 1, square root that. Again, you won't have to memorize the equation, just understand what the parts mean. It's funny how often I see on exams that people, I guess they don't know what the parts mean. Because they're like, well, the equation in the exam will have the equation for me, so I have to learn everything. You still have to know what X or K or N or capital E mean if you're going to get any sense out of this. That's what I'm more interested in you knowing. Any questions? Okay. So that's hypergeometric. Let's do Poisson. Poisson has nothing to do with this.
I'll get rid of that.
Imagine that you have a restaurant and it's the summer and you're trying to estimate how many people will come into your restaurant on any given week. Now, over the course of 1 week, how many people can come into your restaurant? What's the maximum number? You don't know. Great answer. You don't know, right? It's a lot. If I did 1,000 coupons, though, what's the maximum number of coupons that can be redeemed? 1,000, right? So when we do binomial and when we do hypergeometric, there is a natural limit. You can't have more successes than you have trials, by definition. But Poisson, that's different. Poisson sets up an interval, a week, in this case, and then says, how many successes can we have? What is the likelihood of getting 20 successes, or 500 successes, or 300? There's no natural limit. Poisson sets up an interval. It can be an interval relating to time, a week, for example, or it can be an interval relating to space, a geographic area, or the amount, or like the length of a chain. If the probability of success, and it requires a couple things going on, like the probability of success. In each interval is identical. So this is why I set it up as a week for the restaurant, because the probability of having a customer show up on Saturday is very different than the probability of having a customer show up on Wednesday. It's going to be a weekly cycle. So I set it up a whole week. The probability of a customer coming up sometime in the week should be the same versus whether you're talking about 1 week versus another week. Granted, even that's not technically true. Like early January is going to be different than late May. But over the course of maybe a particular summer, it might be basically true. Two. Intervals cannot overlap. So if we're setting up a geographic area, we can't do that where there's some double counting of that area. And they technically should be the same size because that would make the probability the same. All things being equal. Any questions so far? Okay. Occurrences in each interval must be independent. In other words, just because someone came to my restaurant in week 1 doesn't make it more or less likely someone will come to my restaurant in week 2. Typically, in the notes, and maybe I should actually make a distinction here, just to make this clear. What's interesting about Poisson is it's defined solely by this, lambda. Lambda is the average number of successes in an interval. When I was using probability of success, it technically should be lambda, or mean number of successes. Or this is, in each interval is an interval. It's the same. But because, like, you know, the probability of success and mean number of successes, that's basically the same thing. That's not necessarily too confusing. Right? I can't imagine a scenario where the probability of success is the same, but the mean number of successes is not. I mean, I guess you have different trials or something, but it's basically the same idea. But just for completeness and clarity, technically it's the same mean number of successes there. Sigma is also really great, it's just the square root of the mean. That's nice and clean. I'll actually define lambda. Lambda is the average number of successes are unusual. Any questions? Yeah. Oh, so if we had overlapping intervals, we'll sort of be double counting a particular point. And therefore, is that if event happens, if something happens, if say someone goes to this particular place, does that count for this one or does that count for this one? The whole idea is that it sort of feeds in this whole idea of independence. We have to have clear separation between intervals. Great question. Any other questions? Okay. Let's dive into Excel. So, before we get too deep into it, I'm trying to find an example of this. There we go. Before we get too deep into it, I want you to take a look at this equation. This equation is what you'll be working with when you do Excel, but you will not use this equation. You won't even see this equation. You won't directly, I'm saying you will be using it, but you won't know you're using it. This is the equation Excel uses. If you're using a binomial distribution and you want to figure out what's the probability of getting X number of successes, let me hit the light there. What's the probability of getting like 20 successes, or 5 successes, or 5 million successes? It's using this equation. So that X becomes the 5 billion successes. There's our N for the number of trials. There's our P for the number of the probability of success, our Q for the probability of failure. You can see all the parts here. The resolution isn't great, but you can see all those parts here. So appreciate what Excel is doing for you, because this is a real fucking pain in the ass to do by hand. It's great just to be able to put in a command. And everything that's got. Does anyone know, by the way, what this is right here, this equation? What the exclamation points mean? Combinations. These are combinations. And what is the? I'm sorry. What does the exclamation point mean? So this is the combination equation. What does the exclamation point mean?
It's like n times n minus 1 times n minus 2 times n minus 3.
Exactly. So how do you pronounce it? Do you just say N really enthusiastically? N!
N factorial.
N factorial. But yeah, you're right. So it would be, in this case, 5 billion times 4,999,999 times 4,999,990. Oh my God, kill me now. There'll be some canceling, of course, but in general, it'll just be a pain in the ass. Now, I want you to take that equation. Keep that in mind that that is often abbreviated as something that, I can't remember the exact order, I think it would be like this, right? NCX would be this right here. This is the equation for hypergeometric. Appreciate how many C's there are. One combination equation, another combination equation, divided by another combination equation. Yeah, his eyes want to pop out of your head. All right, that's a lot of factorials. This is also a huge pain in the ass, even worse. The good news again, Excel has this built in. So I only show you these two equations not because I expect you to do them or memorize them or even be familiar with them. I just want you to be aware of how complicated they can be, how complicated they are, so that you appreciate how great Excel is. All right. With that in mind, open up a blank Excel document. Let's work with this. So, let's go back to my original question. I wanted to know, what is the, if I issued 1,000 coupons, how many coupons can I expect for your team? Maybe this is, for example, a coupon for some sort of like, I don't know, theme park. And I want to know if I'm going to have a lot more people show up. Or maybe this is a coupon for a pizza place. I want to know how many more ingredients should I buy. I'm trying to get some idea. How many coupons can I expect? Maybe you can think of it as like a confidence interval too. Like, how many can I expect at least? How many can I expect at most? With some sort of reasonable probability. Okay. So let's start with the information I will need. Clearly, I'm going to need the number of trials. I am also going to need P, the probability of success. I'm going to need X, what I'm curious in, probability of X, or probability of X. And I will also have a cumulative function, just like before. What's cumulative mean? Do you remember? We haven't touched it in a while. What does this mean in Excel?
Counting everything before.
So if I'm curious what is the likelihood of me getting exactly 60 coupons, then cumulative is 0. If I want to know what is the likelihood of me getting 60 coupons redeemed or fewer than 60 coupons redeemed, the or fewer makes that 1. Or if you want false and true. So I issued 1,000. Let's say that there's a 5% chance the coupons will be redeemed. And I'm curious, what's the chance of getting exactly 60? So the exact part makes that cumulative option 0. I'm going to call this piece X. Here's my PX. If you are not sure how to do something in Excel, which should always be your core, how should you do this? What's your question? When in doubt. When in doubt, what should you do if you don't know what to do, Rebecca?
You Google.
Even easier than that. You ask what? Me? No, Google is easier than asking me. I don't know what's available to Google everything. But if you don't know how to do something in Excel, this is a fast way. So let's look at it this way. What's fast and also makes you look like you know what you're doing. Nisha. The what? Well, then it'll just look like you know what you're doing. Yeah.
That's the how much one.
The what?
How much one? That goal next to.
That's what she's talking about. Yeah. Yeah. What? What was that? Uh-huh. And then what? Like, wave my hand around? Hit the thing? What? Well, so we're not going for cumulative, we're going for what kind of distribution do we use? No? Binomial. So let me start typing. Binomial. Right? And then it looks like that you know what you're doing because you just sort of type it slowly and then you know, oh, okay, that's not good. And you just start typing and you never go to Google. We'll think you're less smart than maybe you. That's okay. That's okay because you know it, right? You know the secret trick goes out. Right? Just sort of vaguely know what you want, type equals, type vaguely what you want, and hopefully you get it. Normally, of course, if you start typing days, or days is not going to right? You got a dollar text in the base. So that won't work. But as I mentioned, binomial is distributed, is built in. We also have the binomial range option, binomial invert. We're not going to worry about those. Though I guess you could put in a range. But we're just going to use binomial distribution just so we're most familiar with what's going on. Now, this is the tricky part. It's asking you a bunch of information like number underscore s. What the hell is that? And probability underscore s. One thing is you can probably figure out the underscore s always is a reference to successes. Always a reference to success. But if you're not sure or if you don't feel comfortable, another thing you can do is hit this FX button right here. And that FX button pulls up a window which gives you all the details you need. Now that my cursor is in number S, it tells me number S, oh, that's the number of successes in the trial. Or in trials, I should say, in all the trials. What would that be here? 60. Why do you say 60?
Because you want to know the probability of getting 60 coupons.
Mm-hmm. Yeah, absolutely. I want to know the probability of 60 coupons you need. So put in 60 there. What's trials, Jeanette? What's trials? What should that be? N, which is 1,000 or D1. I like to put in the because I know you can change it really easily. You can see how it changes. Okay, what's the next thing? Probability, which is exactly 5. And the cumulative option is going to be what? Xiaoyang. 0. Or D4. So what's likelihood? And you know, immediately it tells me what the answer is right there in the lower right-hand corner. But you can also just, okay, yeah.
How did you pull up that window?
I hit this FX button right here when I was in the thing. That FX button is great. And we get about 2%. There's about a 2% chance that 60 coupons will be redeemed. Well, that doesn't seem very likely. What is about the 50% chance? If I put 50 in? I think we're done. 50 is the average. Remember, 50 would be the average. 50 would be 0.05, the probability, times n, the number of trials. 1,000. 1,000 times 0.05 is 50. So we get about 5.8% chance there. Doesn't change very much. Maybe I see we can sort of just at 60, because 59 also matters. 59 is not much different than 60. Maybe what's the likelihood of me getting somewhere between 40 and 60 coupons redeemed? How would I figure that out?
Do 60 cumulative 1, and then subtract this from 20 cumulative 1.
So I'm going to make 2, because I'm trying to work with 3 numbers here. So I just copied this section right here and pasted it right here so I have the same thing. Therefore, I can put 60 for one and 40 for the other. And then I can put in that. Question
minus 40. Oops, that's weird. Oh, you're right. Nice. There we go. Now I'm right.
This is where the language gets really important. I'm gonna erase this part up here. I want to keep. Oops. I want to erase all that. There were the 3 requirements I was going to highlight, but I erased one of the requirements for Poisson. Okay, I guess I don't really need this section.
So these POS, do the answers info or no?
No.
So like it's gonna get like you're gonna use don't have the 99 or like one standard or one
Yeah.
standard deviation.
Yeah, because keep in mind we can't do it this way because, you know, you can't be less than 0, but we can't be all the way up at 1,000. And the average is 50.
So it's way less.
So yeah, it's way skewed, right? That said, we have this other issue. So this is 60. This is 40. I calculated this, the 60 or fewer, which is right here. And I want this at least 40, no more than 60. If I do 40 for that second one, am I getting this?
You need to see what like less.
Because if I put in 40 here, like I do in this next section, I'm calculating the chance of 40 or fewer. I'm removing 40 or fewer. But I want to include 40 in this distribution. I want to do 39 or fewer. Now you might say, well, David, but then you're also including the stuff between 39 and 40. And you're right, but I'm only working with whole numbers. Right? It's a discrete probability function, so it's okay. If this was like cumulative, then it really, then I really wouldn't matter. Like, who cares? But because this is discrete, it can actually be pretty chunky. So we'll do 39. And it goes up a little bit higher, because now we're including the 41 before we work. Any questions? This is kind of interesting, right? An 87% chance that I will get between a 40 and 60. There's a 93% chance I will get a 60 or fewer. Which means, of course, there's about a 7% chance I'll get 61 or more. Depends on how cheap my ingredients are. Yeah, pizza dough, I can probably freeze it. Maybe I'll get extra pizza dough. My worst case scenario, I just freeze it, it's fine. But this is something wrong. Any questions? Yeah.
All right. So the question was like more than 40, less than 60. No, don't do it the first time.
Yeah. So if I did, if I did something like at least 41,
Okay.
right? But no more than 60. Yeah, absolutely. Any other questions? Okay. Let's do another one. I want to play around. I want to do a different one than what I did in the let's do another example. Let's imagine that we work in human resources and we have 25 applicants for an engineering job. And of those applicants, 6 of those applicants are female. We have 6 female applicants, and then we have 25 applicants in general. Let's do this. Oh, I thought like before we move on, for those of you who might want to see the whole thing. That's what I did just now, in case you missed it, for the binomial and to find the differences. Just so you know. All right. Going down here. Oh, okay, so we have 44 applicants. Imagine 5 of them move on to the next scale of the interview. So we have 25 initial applicants for the job posting. We're looking at all these applications, trying to figure out who to interview. We can only interview 5 of them. What do you suppose the chances that one of these applicants is female? And before I get too far into this, note, this could be used to identify instances of sexism. That if maybe the HR department is sexist or the engineers maybe reviewing the applications are sexist, we could identify, and none of the females move on, only one of them moves on, we can say, well, what would be the chance of that, just by random chance of that happening? And if the chance is shockingly low, that none of them move on, we could say maybe they're being sexist. If the chance is pretty good that none of them move on, then maybe it's not sexist. So it gives us a way to identify red flags. There's one application of this. Now, note also, this has to be hypergeometric. Why does this have to be hypergeometric?
When one moves on, that person can't move on again.
Yeah, exactly. There's no replacement. And when I select someone of these applicants to move on to the next round or to be interviewed, I should call that interview. Rather than move on. If I select one of these applicants to be interviewed, then that means I cannot select that applicant again, and the probability has changed. Especially since I'm also ultimately going to be selecting 5 people, which is 20% of my pool. So that's going to be way more than 5%. So, can I do that? Can I say x is 0? Can I say x is 0?
No, because then you're looking for no people, though.
Yeah, why not?
Because then you're not looking at anybody who makes it.
Well, wait. So this is my capital N, the number of applicants I'm working with. What is a success? Female. Absolutely. This is capital N. This is the number of successes. What is interview? Anyone, what is an interview?
Trials.
The trials, absolutely. That's a small n. And then x is just x. In other words, I am saying, in fact, we can even call x females interview. Can I have 0 women interviewed? Absolutely, yeah. This is what I could use to figure out what my what's it called? This is what I could use to figure out if this is sexism or not. Look, you had 5 female applicants of your pool of 25. 6 female applicants of your pool of 25. You interviewed 5 people. None of them were women. Maybe that's sexism. Maybe it's not. Maybe, as a first stage, if it's likely that that could happen by random chance, then maybe it's not sexism. If it's unlikely, then maybe it is. So let's find out how likely it is. What's the probability of X? So what's the secret? Start typing. Hypergeometric. There it is. And again, if you're not sure what all these things mean, we can always just select FX. So the number of successes in the sample would be 0, be 12. The number in the sample is 5. That's the number that we interviewed, be 11. The population of the successes in the population is 6, or be 10. The number in the population, or the number of applicants we're working with, is be 9, and cumulative is 0. Okay. Actually, there's a 22% chance. There is a 22% chance that we just won't get any money. Not because we're bad people, but just because it just didn't turn out that way. That doesn't seem that low. Can you pull up of course, the equation. Yeah. That doesn't seem that low. Maybe you can argue it's still like, it's still kind of, it's still pretty low. So like 50%, yes. So that doesn't seem that unlikely. So I happen to do it. This is the reverse order of what it is in hypergeometric, because that's just how it worked out. Except for the cumulative at the end. Yeah. Oh, sure. Oh, great, that's awesome. Like that. Any questions? Okay. What happens when I make this from closure to 1? What happens if I make this a 1? What happens if I do that? Goes up? Didn't change at all. Why did it change? Why did it not change? Keep in mind what the cumulative function represents. The value or less. We're looking at 0. Okay, do you have exactly 0 women interviewed? Do you have exactly 0 women interviewed or fewer than 0? Well, since you can't get fewer than 0, in this case, no, it hasn't changed at all. So we can put in 1 or 0, it doesn't matter. But appreciate though what happens if we didn't have 6 women interviewed. What happens if we had 10? Now it's only like a 5.6% chance that by random say, ooh, that's suspicious. Imagine if we had more than half the women with it and none of them. That's a less than 1.5% chance. That's really suspicious. You had 13 female people out of 25 applicants, and you interviewed 5 people, and none of them were. That's strange. And now we start to get maybe there is something shady or ethical going on there. And then one more to the more investigation. Any questions? Let's end with Poisson. The south of London, 1944. During this time, the Nazis are assembling these flying bombs, and they are shooting them over the channel and landing in the south of London. Now, in order to protect against these bombs, they organized the south of London into these districts. The districts were of equal size. I'm not going to draw them of equal size because that's kind of boring and it's hard to do. But the districts were of equal size. And they were used in order to protect against fires, right? People were actually assigned, buckets, and were going out there They were on patrol. They were watching for things. If something landed in their district, if a bomb hit their district, they'll take out the fires. But there was this question. In fact, actually, we had how many districts did we have in all? I think it was 576. 576 districts or regions. But there was this question: could the Nazis aim these flying bombs? Could they have some sort of capacity to aim them, whether in flight or before they shot them? Maybe they could figure out. That's important because if they can aim them, then you want to put more emphasis on these targets, on these vulnerable targets. If they can, then you want to distribute your protection all over the place evenly. Well, there was a statistician. He gathered some data just after the war. I think it was 1946. He gathered this data. So you want to see, could we have used Poisson's distribution to figure out if they could fire these things randomly or not? Could they aim them or not? Well, there were 535 bombs dropped on London of these flying bombs, dropped between, it was, what was the exact date? June 1944 to March 1945. The south of London. That means, on average, how many bombs were dropped in a particular region? How to figure that out? What is 535 divided by 576? Is that there are 535 bombs? That's 576 regions. That's about 0.93 or 0.929 bombs per region. So each region should, on average, get 0.929, just slightly less than 1. Because these regions were the same size, the likelihood of any bomb dropping in a particular region would be the same. So the average was going to be the same for each region. And the regions did not overlap. And just because a bomb landed here doesn't make it more likely that a bomb will land here or less likely a bomb will land here. They can't tell. They're just shooting them across the channel. They're not in the area, so they can't communicate. So if it is random, it should follow a Poisson distribution. 0 bombs in a district, 1 bomb in a district, 2, 3, 4, 5. We'll leave out the 5, then 5 more. So if I wanted to figure this out, I would type in Poisson distribution. X is the bombs in question, 0 in this case. This is our average, which, because I don't want to have to type in 0.928819 for per, and I want to drag this down. But I don't have to keep, but I can't, if I drag it down, then this is going to update to B20, and I don't want that to happen. How would I make sure that this stays this reference? F4. And finally, cumulative, because it's we're looking at exactly that number of bombs. Double click. There we go. We can, even if you want, we can convert it to percent. That's some decimal places. There's about 40, almost 40% of all the districts should have had no bombs dropped on them at all. About 36.7% would have exactly 1 bomb, 17% for 2, 5% for 3, and 1.2% for 4. We can do 5. Like, when you're working with a 1 for average, it's like 5 seems really high. So we can clean up. So we're just going to leave that for now. We're just going to leave that alone. Any questions so far? Let's do the expected. Yeah. Oh, of course.
What F can you get?
F4. Or you can just put in the dollar sign. Now, what I'm curious about is if there should be, and I can have about 40% of districts have 0 bombs. How many districts should have 0 bombs? How many districts should have 0 bombs? Well, it'll be 40% times the number of, I guess, of regions. How many regions should have 0 bombs? 576. Then we can use that to find out how many regions should have 1 bomb, how many regions should have 2 bombs, how many regions should have 3 bombs, and how many regions should have 4 bombs. And note what I'm doing is I'm purposely not showing you the results yet. I'm just showing you the calculation. I'm going to shrink this now. Now, fun stuff for us, we actually have how many regions have different numbers of bombs. I found a paper on it. Oops. This is the actual, and I don't have it memorized, but I have the actual right here. 229, 211, 93, 211, 93, and 35 and 7. If there was one that's a 5 or more, that's fine. That was a standard. You don't need that district at 5. That sucks. Okay, let's see how close it was. Let's get rid of the show formulas. We don't need the formulas anymore, right? We're good? All right, let's see how close it was. That's still easy to read. $227.5 we would expect. Actual was 229. 211.3, actual 211. 98.1, actual 93. 30.4, actual 35. 7.1 theoretical. 7 actual. This is pretty close. Yeah, I think this is amazingly close. A little bit right here, but otherwise amazingly close. In other words, here's statistical evidence that the Nazis could not aim the flying bombs. Because if they couldn't aim it, it was random, and what we actually saw followed a Poisson distribution as if it was random. Right. Any questions? Okay. I will see you then on Thursday for review. Have a great couple of days, everyone.